Hello everyone, welcome to 5-minute scientific computing talk. In this video, we will introduce the oct-tree, which is a really important and useful technique for the space partition. Let's dive into details. The idea of the space partition is really simple, and for this example, if we use line, plane, and cubic as three concrete examples, and have two levels of hierarchical data structure, let's look at how to partition it. For example, for a line, we have start point and end point for the level 1. And for the level 2, we may divide this line into two partitions, and we have S1 and 1, S2 and 2. So we come from this point, we can get two segments from this segment. So there are two branches here. And for the plan, because we have two dimensions, if we partition each dimension by this way, and the result is that we can get a space with 4 specific partition or small areas. And by this way, for each small areas, we can use the lower bound and upper bound to represent it. So we have two pairs of lower bound and upper bound. So we get 4 specific lower bound and upper bound from this large space. And so there are 4 branches. And similarly, for 3-dimensional space, we can get 2 to the power of 3 equals to 8 specific areas. And if we try to partition it along each dimension, this way, and this way, and the result is that we can get 8 specific subcubic. And for each particular space, we can still use a particular lower bound and upper bound to represent it. And this is the idea of the oct-tree. For the parent node, we use lower bound and upper bound to represent this large area, large space. And at the second layer, and we have basically 8 branches. And for the node of each branch is a specific particular areas. Basically, we refine this large space step by step. For example, we can also have level 3 and level 4 if we like. For example, we can still refine this part and still cut this into 8 spaces, into 8 specific regions. Okay, let's look at a real example. And this data set is called treemesh.vtk. We get this data set from this repo, vtk example source testing data tree mesh. And if we load this data into the Paraview, we can check that it is organized in a hierarchical data structure, and there is the different color labels, different oct-tree levels. The outermost layer is the blue color, and then we can refine the mesh cells and get really dense cells here. And this is the result, and we can show that how can we move from the point cloud to this data structure. And first, let's try to extract the point cloud from this data structure. We can add filters such as convert to point cloud and apply. Yeah, if we show these results, we can see we get a lot of point here, and the point, so those points are organized in different density. In the middle layer, there are lots of points here. And the idea is that we load this data into our program and try to build a boundary or the oct-tree index based on this data set. Let's first save data such as point cloud. So we already stored that. It's okay. And this is how we process the data. This is our program. And firstly, we load that file and we use the poly data reader to load this point cloud. We can check the information here. The type of this point cloud is polygonal mesh. And next, we get this data sites from this reader. And this part is important. We use vtkOctreePointLocator and cite this grid as the input of this data set. So this means that we want to build an index based on this input data, and we build the locator, which is a kind of index based on this grid. We didn't modify the data sets, we just add another layer, which is called the point locator. It's a kind of index based on the oct-tree. We can print this oct-tree data structure, and furthermore, we can also use this function generate representation and to show each layer of the boundary. For this result, it only print out the boundary instead of the actual data set. And then those boundaries also polygonal data. We can output it and check the results. And let's say here we can put this point cloud into the remote machine. And then this is on my remote machine. And you can see that I have already built this vtkOctreePointLocator test program. Let's see how it works. And we input the point cloud data. You could see that we print out the data structure of the oct-tree in each level. Here, the default level is, I believe it is 5. Let me see. Yeah, oct-tree level is 5. And we get several files here. Test points oct-tree. Let's remove those files and do it again. Oh, we also need to put here. Yeah. Those are polygonal data generated by each layer of the oct-tree. Let's put those data, move those data to the local machine. Point cloud. And then we can load those data and put them into the Paraview to see how it works. Point cloud. There's on 1, 2, 3, 4. Let's see. Yeah, you can see that this is a level 0 zone results. We can show wireframe. And then if we show the layer of the, if we show the first layer, we don't need to show those parts. You can see that the original region is divided into 1, 2, 3, 4, 7, 8, 5, 6, 7, 8 subregions according to the idea of the oct-tree. This is the second layer, first layer, second layer. Those specific region are the child node of this first region, and then next layer, next region, next level in the oct-tree. Yeah, you can see we refine the cells step by step, and if we show our results here, you could see that we could get really dense frame at the inner part. That is the idea of the oct-tree and how it works, and how do we build this data structure, those kind of boundaries based on the input data. By using the VTK, it is really simple. Just use this data structure. And okay, for the next step, let's maybe dive into this oct-tree point locator and to say how it works. And if you understand the idea and some implementation, we can implement our own version of the oct-tree. Okay, before diving into details of the source code, let's look at a small and important technique, which is how do we index for the child nodes. Let's start with a simple example for a line. If we divide it into two partitions, and we want to cite index for each partition, we can simply use one digit. And if a particular region is lower, the value here is larger than this pivotal point, we can cite it as a index 1. We just need to use one digit. And similarly, for this half part, we can set it as a 0 zone, which means its value is smaller than this pivotal. Using similar idea, we can index the subregion for the two-dimension space for each dimension. If for example, a point here, its value is larger than the middle points in this dimension, and the value is smaller than the middle point for this dimension. So let's assume this is the first dimension, this is the second dimension. So the index for this region will be 1, 0 zone. And the index for this region is 0 zone, 0 zone. And for this region, it is 1, 1. And for this part, it is 0 zone, 1. So those are all the binary numbers. We can also transfer it to the decimal numbers. This is 3, this is 2, this is 0 zone, this is 1. The benefits for this kind of decimal format is that we can put it in an array and use the index, and then we can map this index to this spatial location. So the important thing for this index is that we build the connection between the space location with the particular index. Similarly, for the 3-dimension case, we also use the similar strategy. For example, this is first dimension, second dimension, and third dimension. If the value is large for first dimension, if the value is larger than middle point, it is 1, and here it is 0 zone. For the second dimension, and still the same thing. Then this is a middle point, and here this is 1. This half is 0 zone. This is the middle position, and for the third dimension, similar thing. This part is 1, this part is 0. So let's try to compute a particular index for a region. Let's say this region. What is the index for this region? And for the first dimension, it is 1. For the second dimension, it is 0. And for the third dimension, it is 1. So if we use decimal value to present it, it is 5. And similarly, we can calculate different index values from 0 to 7. Okay, let's look at how vtk implements the oct-tree in some source code. And this file defines vtkOctreePointLocator node. It defines a node for this tree. And you could understand it quickly. We do not dive into details here. And this file, this data structure, vtkTreePointLocator, use this node to build the tree. And we just show the core function here, which is how we partition the region and build the tree. This function is a typical recursion function. You could say here, we call the divide region function in a recursive way. And this 8 means we get 8 subspace. And at the first part of this function, it tests if the current case satisfies the recursion condition. If it does not satisfy, we do not further do the recursion and to divide the region into subspaces. We use this divide test to say what is the condition for the recursion. You could say the one condition is that if the current level larger than the max level, we do not do the recursion, or if the size of the points is, if the size of the points is larger than the default, the specific value, we still do the recursion call. Those are the general rules. And then assume that we do the recursion call, we increase the level, and then this node helps to create the child nodes. And number of points is represent how many points do we have in the current level, and we get this data set. For example, we start from the scratch. At the first layer, this number of points represent all the points in our region. And this oct number of points represent how many points will be in specific subregions. And this array try to record the specific index for each region. For example, those two data structure is important. This one records the number of points, but it does not know which one is in which area. And this is a 2D data structure. It represents the specific index for each point in each dimension. And this one is important. It gets indexed based on the position of the specific point. Let's look at this function. You could say that it basically goes through the 3 dimension, and if the coordinates of points is out of this boundary, it returns -1, check containment. And for here, it uses the index techniques we discussed just now. If it's larger than the middle position, we set the specific digit as 1. Otherwise, we set it as 0, so we can get an index. With this index, we can set it to the associated position in this point array, and also increase the number of points. And then for those data structure here, for those parts here, we just basically reduce this ordering array and set it as a new input for the next recursion call. And I think the idea is simple and there are some details, but I believe that if you check it in details, you will understand how it works. And furthermore, you could follow those steps and write your own version of the oct-tree. Okay, that's all for this video. Thanks for watching and see you next time.